we will see that foundation models are all about learning representations that in a kind of self-supervised manner or unsupervised manner from the uh, speech data. Now the question is, you could ask yourself, is it so new, or what has been going in the research community? So I try to give a little bit an overview first on how these representation learning things have evolved to speech foundation models. Then in the second part of the talk, I'm going to present some of the works that we have done recently, and try to kind of give a flavor like what kind of opportunities and it presents. At the same time, there are many challenges associated to it. So I thought of like giving a little overview through a few select studies in that. And so, so, so the first part is that I believe that many of you are already aware of speech processing. So in speech signal, we know that the signal is non-stationary. So what we have been doing is that we take the speech signal window of 20 to 30 milliseconds typically, and in within that window we can presume that the vocal tract and the source information, those two aspects are kind of stationary, quasi-stationary. We can assume that, and then basically you can apply your speech production knowledge to separate this information that is related to vocal tract system, which is the form and structure I am pointing here on the screen. And also you could also get information related to the source by doing that. So you can use linear prediction analysis or caption analysis. So you do it over 20 or 36 millisecond window, and then what you do is basically you keep shifting the window and keep analysis and extract the features and so on. Now, within this feature extraction process, what you could do is you can introduce some kind of auditory modeling or sound perception knowledge, such as critical bands, which is what happens with the PLP and PLP and um, um, PLP analysis or MFCC analysis. So you have a critical band, and then you apply the idea that we a nonlinear compression, saying that the ear the our ear responds in a nonlinear fashion to the sounds we are hearing, that the intensity and the loudness, there's a cubic root relation or logarithmic compression. This kind of analysis we apply, and this kind of sound perception knowledge you're introducing. And when the neural networks started coming up, so initially people started with like, take a feature, you extract these features. This is what I was trying to explain. Like you extract MFCCs or you do perceptual linear prediction. You can estimate temporal derivatives. This is the delta and delta delta, and then you feed it to the neural network. Yeah. Now this process was started getting questioned, and so this is what we were trying to do. Now the question was, do we have to do all this way of feature extraction, which is what we will see first in this part of the lecture, or sorry, I have to, sorry. I'm sorry for the interruption. Sorry. Um, so the question is whether we want to go all the way through this processing and then feed it to the feature classifier. And then the question is that, is it the only way to extract features? like based on signal processing. So this kind of thing started being questioned, but it is not that it just started now. So one of the first learning based feature representation perhaps happened with what people try to do in the speaker verification community was that you take the features and you try to model them with Gaussian mixtures. And then what we in the speaker verification systems in those days, what people were trying to do was that you train a universal background model, like a lot of data from many different speakers, but these speakers are not absorbed by the system. You train a big Gaussian mixture model, and then you can adapt it with the particular speaker's data, and then you get what is called the means, and you can concatenate the means of the Gaussians of the adapted model, and then you can use that as a feature. So basically, so instead of taking MFCCs and so on directly as a feature representation, you basically go to statistical modeling and you use the statistical model's parameters as a feature observation for speaker verification. So this is one such first approach of how people were moving towards exploiting data and statistical methods together to extract feature representation. If you go a little bit back, actually people were already trying to cluster isolated words and so on based on k-means and vector quantization, all those methods they were applying. They were doing such kind of feature representations. So then yet another such clustering based feature representation is what happens with what's called the compare features, or the bag of audio words based representations. So what you do is you extract what's called low level descriptors. So it can be like MFCCs, your jitter, shimmer, all those things, your frame level information, you extract them. And then what you do is you create a k-means, you cluster them. And then what you do is that instead of representing those features by continuous value or the feature vector, what you do is you basically assign the labels of those k-means as the features. So you can create an histogram. So the idea is, for example, you have a feature, say any dimension you have, a d dimension feature. What I do is I cluster it for, say, let us say that I have 256 clusters. Then what happens is that every feature vector, I can figure out which is the closest cluster and I assign that label. And in this way, I have a fixed length representation for the whole. I can create a fixed length representation by normalizing all these histograms, saying that how many times I see each cluster in my speech data. Now, this is what they call bag of audio word approach. So this approach is again, we're trying to look at, you take the features, but you don't directly use the features, but rather you go to this like what I was talking, like the GMM and so on. Instead of GMMs, we are vector quantizing the data, and then you use this quantized representation as an input to your classifier. So this has been successful for emotion and many paralinguistic tasks and so on. This approach has been very successful. That are you able to follow my presentation, or I am too fast or too slow there?
Yes, it's okay, sir.
Is it okay? So please don't hesitate to stop me in case I am overshooting, yes, or it's not understandable there. Now there was yet another. So this approach is what I was talking is more like clustering based. You can do unsupervised way, this kind of approaches. So then there was also a supervised based learning based representation. So this is like a very old approach, tandem features and so on. And it came in 2000, but if you go and dig a little bit more into the literature, you'll find the idea was there already in 1992. So the basic idea what people were working at that time was the neural networks, they are very good indiscriminative approach. It doesn't need much prior assumption on the data, and it can model long temporal context and so on. Whereas GMMs, Gaussian mixture models, they were generative models, and they can be easily adapted. And when we were doing speech recognition back then in 2000, modeling context dependent phone units using neural networks was not still so successful at that time. And so people used to show that, oh, with GMMs, we can get better speech recognition systems. At some point, what happened was the tandem features started trying to put these two abilities of these two different statistical methods together. So what it was doing was the tandem approach is that you take the acoustic feature, you first train the neural network classifier. Here it was a phone classifier. You are training the phone classifier, and you take these phone probabilities or the linear output of the neural network. This is what the linear output before the nonlinearity, or you take the output posterior probability, you do a logarithm operation to kind of Gaussianize these features, and then you apply what's called PCA, which is also called Cardinal Low transform, and then you get a set of features. Now, these features, they found that it's quite robust to noise, and it can introduce, it is much more complementary to even the features you give as input and so on when you give it to GMMs. So this was one of the approaches where you went towards what's called supervised learning. So you train this neural network in a supervised classification manner, and then you process the output of the neural network and feed it to the GMMs. Now, there are many different ideas emerged. So here I'm showing with the output layer representation, but then people also looked at hidden layer representation, bottleneck representation. So many such ideas emerged just around this idea. So they were all playing around speech recognition at the time, because this was one of the core problems people were trying to solve. So they started looking at what could be more robust features. For example, this whole neural network could be trained on multilingual data, and the GMM could be trained on the monolingual data, for example. And we were quite successful with this in the US DARPA programs and so on. We were quite successful with this kind of method. So where we could show that we can use all the auxiliary data to train this neural network, and then you just train the GMMs and so on the target data problem. So it kind of, so you start seeing that. So you see, we started exploiting this amount of data. For example, this neural network back then, I'm talking in 2005, 2006 itself, we were training it on 8,000 hours and so on. But they were shallow networks compared to today's deep networks, like with 3 hidden layers or 4 hidden layers kind of networks we were training, and we were quite successful with this kind of feature representation. This is for speech recognition. Yet another feature representation that came for supervised learning based representation for speaker was you take the input feature sequence, and then what you are doing is that they are of varied length, T. So you can keep changing. If I speak one time, I get 100 frames. Another time, I may get 150 frames. So what they were doing was they feed to put many frame level processing layers. And then they are doing what called stats pooling. I believe that many of you are already aware of this kind of pooling methods in the neural network. And then they add a hidden layer, and they were trying to classify speakers at the output. So you can train. So like the GMMs, what I was talking here, you're trying to adapt it to a particular speaker. So instead of using the GMM in an unsupervised way, what they were trying to do, you take the whole data, what you have for the universal background model, and you train the speaker classifier on top of it. And then what you can do, you can take these features, what you can do is that instead of using these input features as a representation, you can take these hidden embedding layers, which are the segment level representations, and use them for speaker verification. This is still successful, quite successful method, right? So some of you are working on speakers. This is again, it's again going in the same direction, but here we were doing for speech recognition and finding a hidden representation, feeding to another statistical modeling method. Here, what we are doing is that we are doing training it on speaker classification and then extract embeddings and feed it to the next level of modeling. Here, it could be cosine distance, or you do PLDA and so on. So this is yet another approach. The third approach, again, came in the feature representation learning, is what's called auto association neural networks, or what called auto encoders. So what this kind of neural networks, I am sure you are all may have already aware that you take an input and you predict the input at the output of the network, and you can have many such many layers to project these features. So you can see it from, and then you may have a compression layer. So one up to the compression, you can say it's kind of an encoder, and then you kind of decode the space, and then you come to the original space, right? So you go to a compressed space and then come to the original space. Now, there's a full theory and so on, which is not the purpose of this talk for me to go into detail. That if you have one hidden layer, you can show that it's pretty much equivalent to do a principal component analysis. One compression layer, just one compression layer, input compression layer, and this you may not do any better than that. But having more layers can lead to other type of representations. And there are different types of autoencoders, variational autoencoders, and vector quantization. Again, this is kind of a method where you can see this is kind of a self-supervised approach, right? So you have an input, and the input itself becomes a supervision at the output for you. Yeah. And you try to learn an intermediate representation, which is, if you do properly, if we do a proper analysis, it would come to some kind of principal components. Here with the hidden layers, you can see it can come to like nonlinear principal component representation. Now, then there's an approach that we started at the Idiap while back in 2011, was that okay, that we have to extract the features and then give it to the neural network because they are becoming popular, but neural network could actually learn these features. So why can't we do directly feed this speech signal instead of feature extraction and all to a convolution neural network, and then out after that you have some kind of dense layers, or you want to have BLSTM and dense layers, it's your choice. Here I'm just showing that we have a CNN followed by dense layer, and you predict directly the task. So if I want to do phone classification, the output is phone classes. If I want to do speaker classification, or the output is speaker classes. If I want to do emotion recognition, I can classify the emotion classes like that. Now, why we started looking at this way was that whenever we do signal processing based approaches to do extract features, first is that you are going to make this assumption of quasi-stationarity. Second thing is that our way of feature extractor is 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 assuming some kind of a model. So for it, what it assumes is like you have the input vocal fold vibrations are convolved with the system and then get you an output. And now you're basically trying to deconvolve. So you're assuming a model for the signal. Now this model has been successful, right? So it has been successful for speech coding and so on. But is it the model for everything? So we went for MFCCs and all these features. So we were doing that, and it was not sure that is it the only way to model the information from the speech signal. So what we started asking, so okay, it could all allow us overcoming some of the limitations, what I'm talking about, this short-term window-based processing and so on. It may also allow us to better understand speaking characteristic that are task specific manner, because when you extract the features such as MFCCs and the PLP capital coefficients, all these features, often you're not thinking about the task. You're applying your understanding of this source system decomposition, capturing the envelope using the capital features, or adding the fundamental frequency information. This is based on the signal model, but as I said, is it the representation that is suitable for all the problem? It's not sure, but we were successful with those kind of representation. But that was also a limitation for us. So we started this work. So what it happens is it uses minimum prior knowledge. It still doesn't obviate the idea of not using short-term windowing. It still uses the idea of short-term windowing, and it also kind of interprets that any feature extraction, you can see it is a filtering operation, including Fourier transform, can be seen as filtering operation. I'll illustrate with an example later. You can see it as a filtering operation. So these filters could be learned from the data. And second, the third thing is that context, that information regarding the output classes may not necessarily remain in one particular frame, but it may also be in the neighboring frames. So you can introduce context at the input. Now we will see that the transformers can take all the context in the speech for you. But here, when we started, we were asking 300, 500 millisecond or 2 second, depending on the problem. We could take any context to learn this output class here. So all these things could be also, these are the hyperparameters that sets in this, but they all can be determined in a data-driven manner, and all the stages you could train simply using simple joint backpropagation. If it's a classification method, you just use a cross entropy measure, and you'll be able to train them. Now, this is what the illustration of the how it works in the first convolution layer is that it takes the speech signal, and then you have this small window which you keep shifting, and it's working on samples. And now what you can do is you can control this window size here. So I put this size, controlling this window size as two parts. I call it segmental and subsegmental. If this window size, if you keep it less than one pitch period, I call it subsegmental. And if it's more than one, between 1 to 3 pitch periods, it's like segmental approach. It's like a normal window. So it can be like, if you take a 20 millisecond, it's like a segmental approach. And if you go to like 2 millisecond, around that kind of a thing, where you can presume that it will be less than one pitch period, because if you take a pitch cycle of 2 millisecond, it's about 500 hertz. So most of us we have 400, at the max 400, or males will even have a very low fundamental frequency. So it is what's called the subsegmental part if you take a very short window. So you can control. Again, it allows you to introduce knowledge here, the way you want the signal to be modeled in the very first convolution layer itself. And then you shift them and you filter them to the convolution filters you in that layer, and then you get an output. Then you add another convolution layer, and so on. And this is what it is illustrating here for speech recognition. When we first trained this thing, all these hyperparameters I am showing here, it came through purely cross-validation based grid search and so on. We did that, and this is what we ended up. So we found that for speech recognition, this window is like about 1.8 milliseconds for you. And then when you do the max pooling, after that you're looking at a window of 2.5 millisecond. Then if you do again a max pooling, you're going to a window size of 12.5 millisecond. And then you do again filtering and max pooling, and like this. If you go around the last layer, the third convolution layer, it's like looking at you're looking information at a window size of 90 millisecond. So it kind of allows you to do what's called a kind of a multi-resolution analysis, where input layer you look with very fine way, and the later layers are more modeling the course information kind of step, and then you can classify uh, this system, the classes at the output. Now we were quite successful with many things. So we showed for speech recognition, speaker presentation attack, which is called like today spoof detection, what we call a gender recognition, paralinguistic. Even we could show it for regression problems like breathing pattern estimation from this. What was changing for was that what context you are looking at. For example, speech recognition, we found 250 to 310 millisecond input. This context was good enough. For speaker, we could go from 500 to 2.5 millisecond. For presentation attacks, maybe 300 millisecond was enough. Gender paralinguistics, it was like 250 to 500 millisecond. And for breathing pattern, of course, we need a larger segment of speech. We needed at least 3 to 4 seconds of speech to basically predict the breathing pattern. What we found was something very interesting. If you'll see in this kind of networks, is that again I put this seg to tell you this window sizes that were kind of more of more utility for these problems here. So what was more interesting was that this number of convolution layers, you can go between 3 to 5, 2 to 6, and so on. The hidden layers, we were hardly using one or maximum 3 hidden layers. So this kind of these filters are able to learn the features in such a fashion that the later dense layers, you may not necessarily need a huge dense layers here. So one dense layer was enough for example, breathing pattern estimation. It is the same network that we took architecturally from paralinguistic analysis, except we change the context, we change the cost function at the output because it's a regression problem, and we train it, and it works for breathing pattern estimation, and so on. Now the bottom line is that we are able to neural networks can learn feature representation directly from raw audio. That's what was coming. So the question was, what we were asking at that time was like, what is this neural network is trying to learn for us? So to do that, we did kind of first analysis. So you could take the first convolution layer filters, and you can ask the frequency response of this first convolution layer filters. So this is what the cumulative response. So you take, there are 80 filters, suppose. So you take the Fourier transform of those 80 filters, and you sum the frequency responses, and then you plot this what's called cumulative frequency response. So the first thing what we saw for speech recognition, the focus was in the mid like 1,000 to 3,000 hertz or up to the telephone bandwidth. The emphasis was given to that for phone classification. The input, as I said, was about 1.8 milliseconds. So it was looking at less than one pitch period for adult speech, and it was trying to focus this kind of frequency region. It was giving an emphasis. The same thing if you train for speaker recognition to classify speakers, and you could actually, in this case, what I was showing for speaker recognition, you could go also to segmental, which is thing. So we were giving it like about 18 millisecond speech, and we're training the speaker classifier, and with the context of 500 millisecond, we saw that the filter responses are focusing on very low frequency regions over here. They're focusing on very low frequency regions. Now, this is one way to visualize what information the first convolution layer is kind of it, because as I said, this whole convolution layer and feature extraction can be seen as a filtering process, and it kind of tells, look, oh, it's not looking at all frequencies equally. It's giving emphasis to some frequencies, de-emphasizing some other frequencies over here. Now, this was one way to look at it, but then the problem was, okay, what is really happening after the first layer, between the first layer and the second convolution layer? So here is what I can give an interpretation of DFT of that. So in DFT, what we do in when we take a discrete Fourier transform, we can see that what we are taking is an input signal, and we have a set of bases, sines and cosine bases. This is what is here. I have drawn is done here. What we are doing is we are trying to project the signal to a basis, and you get an output, the projection over here, and then what happens is you can see this projection times the DFT of this basis, or the sines and cosine. Since are the pure sines and cosines, they are going to be delta functions for you, and is basically you can see the DFT as a projection multiplied by the DFT of the basis function, the cosine, sine, and cosine basis functions, which are delta functions sitting at a particular frequency, and you get what is the magnitude or the energy present in that particular frequency. So you can get it. So you can see the DFT operation in this fashion, what I'm trying to show here. Now we can analyze now we can take the same approach, and you can analyze the filters that are in the convolution layer, except that they are not going to be this nice sines and cosine bases. First of all, they will not be a basis at all. They will be more like what we call in if you have go to compressive sensing and that kind of coding areas, it will be like more atoms. So you can see them as atoms for the spectral analysis, but you can apply the same analysis. So instead of this sines and cosine, you replace the filters that are learned by these convolution layers. You put there those filters, and you do the same analysis, what I'm trying to show. So you kind of extract the Fourier kind of the spectrum of the signal. So, and then when we did this, for example, for sound, when we trained the CNN for sound classification, so we trained it on Wall Street Journal corpus, and then what happened is, and then we tried to take a E sound from American English vowel corpus, and I just did this analysis where these filters are replaced by those 80 filters that we were learning for the convolution network. What it was clearly showing was it was trying to focus on those formant-like regions. It was clearly indicating that these filters are kind of capturing already the first two within the first two convolution layers. We are already capturing the formant related information. So here what is interesting is that all this Wall Street Journal corpus was trained on adult speech. So if you do it on boy or girl, child speech, even for them, it was extracting, modeling those formant information for that. So this is what actually we found in the speech recognition problem. Now, once we take this kind of a speaker, now if you take this speaker problem and you do the same analysis here, so you replace the filters that are learned for speaker, and you do this analysis, what we were clearly seeing was if it is voiced, we will explicitly we were able to notice a peak for the fundamental frequency. If it's unvoiced, no such peaks are appearing for you. Now, this is for one frame I'm trying to show. So what we try to do in this network was trained on I think common voice corpus, I think on that. And then what we did is we took another data set where there was a recording of EGG, the electrocardiogram. And what we did is we tried to do the same analysis with that data. And what we could see was indeed
Excuse me,
we
sir.
could,
I
yes,
think there is a one participant, Sandeep. Hello,
yeah.
Sandeep. Do you have any questions, Sandeep?
Sir, one doubt, sir. Actually, whether, sir, is it audible, sir?
Yes, yes, please go ahead.
Sir, whether we are giving the raw speech or it will be converted to some MFCC or like that here.
Mhm. It's a,
Hel-
so here I'm talking about where I'm not doing any MFCC analysis. I'm just giving the raw speech to the
Okay,
CNNs there.
okay, sir.
Is that okay? So
Okay,
I'm
sir.
so now I want to understand what are the CNNs learning for me. So here it is. So I don't give anything. I don't do any kind of feature extraction here. I give it to the CNN, and it's trying to learn everything based on the problem you are trying to solve. So if you are a speech recognition, you may solve. You want to classify phones. If you want to do speaker, you may classify speaker, and so on. You see, so there is no MFCC, is nothing in this process. So that's why we want to know what is the CNN learning for us. Does that
Okay, sir.
answer, Sandeep, for you, the
Yes,
question?
sir. Yes, sir. Okay.
Okay, so this is what I'm trying to show, that if you take the first convolution layer, it can be seen as a linear operation. So you can look it through signal processing analysis, and that's what I'm trying to plot. The filters response is depending upon the problem, and it depends on the kernel width you try to the way you're processing the input layer is processing. For example, where is it, this first convolution layer, how you're processing, it may have an impact on the type of information you are trying to capture. And so what for speech recognition, if you train, we were able to demonstrate that, oh, it neatly focuses on format information in the very first two convolution layers itself. And if you do for speaker recognition, it could purely do things based on fundamental frequency. It was focusing on it. And then we said, okay, is it really happening? Is it for this is for one frame? So we took a data where people recorded the electroglotograph, acoustic data. So we know exactly the closure and opening. So we know the exact pitch. Uh, estimate, and we did the same analysis on that data. Although the neural network did not see that data at all during the training, we could see that for female we can neatly follows the fundamental frequency pattern. For males it's not so good, but the reason could be that the window size was like we were using 300 million, like 18 millisecond. For male it may not be good enough to capture the pitch very like perfectly, the pitch information. So it has to see enough cycles inside that. So this is what the analysis what we did. And then what happens is that if you, for the same speaker recognition problem, if you change this window size to 18 to 1.8 millisecond, it starts focusing on some kind of a format related information as well. And we did similar analysis. So here is an example where we show that there is on the left side is the linear prediction spectrum of and sure. And then what you could see on the right side is the frequency response that I'm calculating in this fashion over here by putting those filters, replacing this cosine and sine basis by those filters learned by the convolution layer. And I can see that you can see that this two it is looking at the merged two formats, is looking at one them together. And here you can see that this peaks and this the other peaks and these peaks are getting modeled by the first two convolution layer. So even for speaker you could change. So what we were trying to demonstrate was, if you keep the window size a bit longer as in the input, it tries to focus on more on the source, it gives emphasis. But you try to reduce the size of the window, it starts also focusing on vocal tract related information. for you. So what I'm trying to drive is whatever we try to do with MFCCs and so on, feature extraction, the CNNs are able to do it for us. Yeah. So they are able to learn such representations and so on. So for the sake of thing, I will quickly browse it, but I'll make the slides this part of the because I have to go to the speech foundation models at some point. So, but what we did, what I've been trying to show here is like one frame analysis and so on. But and we are looking at the first convolution layer, this whole thing, but it doesn't tell us as a whole the neural network what it is learned. And for that, what you could do is you can use some kind of perturbation methods. And the idea is the following, that you take in the input image and you feed it to the classifier, and then you take the output and you backpropagate and ask which input pixels in the image are more informative for the class. If you change them, your class decision changes. So you small variations, how it impact the prediction score. So this is kind of an example. So you have an original image, and then you get what's called saliency map, and it's trying to show that, oh, there is somewhere this regions is where the it is focusing on to classify cat. Another method, deconnet, you can see probably trace there, and you can see that you can see the cat. Another guided backpropagation, again, you can see that it is mainly focusing on this cat kind of regions. Now you can apply the same kind of analysis for the convolution neural network. So this is what the Sandeep's question was. Hey, look, you are giving raw waveform as input, and I don't know what features are it is trying to capture. But if you apply it for speech, what happens is you will get another signal like this, one-dimensional signal. So you take the original signal, you give it to the neural network, and you do this guided backpropagation, and you ask which samples or how much each sample is important for the classification. It will give you another signal. You don't have this luxury what you have in images to interpret by yourself. You get another signal. By looking at the signal, you cannot interpret anything much about it. But then we could show that whatever you want to interpret from this signal could be interpreted directly from spectral domain. So that's it. We can do it. We can show also theoretically that we have given that in the paper over here. So what we can do, if you take the autocorrelation, let us say, of the original signal and the relevant signal, you can see that the autocorrelation is pretty much same. That means it is modeling the information that you may find in the power spectrum of the original speech signal. It is trying to capture. Of course, they are not exactly same for you. And this is for phoneme classification problem. So if you take the spectrum of it, so this is the original spectrum, and we have tried to fit the peaks here to illustrate the format over here, and you take this relevant signal for the E. So this is the left side is the E, what is input to the neural network, and then you do this guided backpropagation, and you get this relevant signal, and you take the spectrum of the relevant signal, and you can see that it is capturing this information of the spectral peaks information is being read. It is containing that, so it is indicating that the neural network is actually learning for you to capture this kind of envelope information automatically, although you're not telling it, please do source system decomposition, do that. But just by training the classifier, it was trying to capture that information for you. Now, again, I'm showing it for one frame, and we could do the whole analysis. So what we train the network on TIMIT, and then we analyze the vowel F0, F1, F2 estimated from the relevant signal and compared it to the original signal, and we found they were pretty accurate. So it was clearly telling that as a whole, the neural network is focusing on this kind of information, which we know for sure for speech recognition. The first two formats are one of the most important aspect, and it is focusing on those first two format information for us. So you can do that this whole network analysis over there, and and then similarly, you can do for speaker. So I'm going to skip the speaker part. So if you do segmental modeling, the window size is long, the pitch is better captured. But if you keep the short window, the pitch is not so well captured in the relevant signal. You can see that. But nevertheless, what we saw is that if you take segmental modeling, it is looking more on the very first fundamental frequency, which I was trying to explain you. And then when you do the subsegmental modeling, what we found was it was focusing on the fundamental frequency region, and then it was skipping some kind of mid frequencies like 1000 to 2000, which are more sound related information, and it started focusing on higher formant regions, which is more speaker related information for you. So the general idea was that we could use such we through this analysis of this whole network analysis, what we could find was we can train and learn directly information from the signal. I'm going to skip this part. So this brings to what is self-supervised learning kind of methods comes. Now, self-supervised learning, so I have tried to show that like we have been trying to work around how to learn representation directly from the signal or incorporating handcrafted feature and statistical methods and so on. So first thing they were doing was they are replacing handcrafted features by CNN based encoder, which I try to convince you all, if you train it properly, it will learn the information that is necessary for the problem. Second thing, what they did was temporal context modeling using transformers and attention mechanism. So what I have tried to show, all the CNN studies, what I presented before, they were all trying to look at a context of 500 millisecond, 200 millisecond, like this. We were trying to make the context, but with transformers, you can look at the whole speech signal as a context. So you can look at the whole signal, and with the attention mechanism you could pick which temporal contexts are more interesting for your problem. Third thing it tries to employ is it's kind of hierarchical information processing. So you have, once you have CNNs that encode that brings a feature representation, after that you can have different layers of transformers. They are kind of hierarchical processing the thing. So which is kind of relates to some way how our information, we also do hierarchical processing, but there is no direct connection to this the hierarchy processing that we have in our brain, that's happening on the perception side for us. But you can emulate that information from one layer to another layer. You can kind of look at different types of information. Most of the methods they are basically what they are based on is that either they are going to cluster latent representation that comes from CNNs or acoustic features, and they're going to predict them. That's what is going to do Wave 2, VAC2, or Wave LM or Hubert, these kind of networks. They're going to do that. And there are different types of modeling: generative, contrastive, predictive, Siamese, and multiple views of data. You can look at the same data in different views when you're learning this self-supervised learning models or speech foundation models, which I call it like that. So what it is, basic idea is that you have an unlabeled data. You kind of create labels through which that's why it's called self-supervised. And these labels can be created by, as I said, by clustering latent variable representations or acoustic features. And then you try to predict them at the output. And in the Duke rows, you're trying to learn a kind of a processing method that goes from the raw waveform do this prediction of this latent quantized latent representation or acoustic representation. So once you have trained them, and then what we are doing is we are trying to give the speech as input, and then we want to classify the you want to do like speech recognition, so you can train the model for phone classification or grapheme classification, and get the sequence of words, or you want to do speaker, you you can adapt this neural network for speaker identification, or even for verification if you want to do. These models could be adapted. So now there is no more feature extraction in this process, right? So, but what I tried to show you before, all these networks at some point are going to have encoders that are based on CNNs for you. So I already tried to show that CNNs can learn representations for you automatically, and then based on how you create this self-supervised learning is what differs in most of these methods. For example, if you take wave to vec 2, what they are doing is they take this output of the CNN encoder, they're clustering them and then using them as a label for with a contrastive loss to train this context network where you have several layers of transformers. But what it does it first step what it does it takes the acoustic representation like MFCC, it clusters and then it trains this context network with this contrastive loss. But then they also now have another loop. First you train like this and then you go to the way of wave to vec 2. So you go to the way of wave to vec 2, and once you train this whole network, then you take the encoder of the CNN and then cluster it and retrain the network, so and so on. And wave LM basically is an add-on step on Hubert for you. And then people also train in different ways, like you don't need to just do with raw waveforms everything directly. So you could also come up with spectrogram as input and predict the spectrogram at the output. There, or what you can do is basically you can strip off some information and try to predict that information. So you can make the network basically the supervision can be changed based on how you want to look at it. So it's not only that you have to look through raw waveform, you can also go with spectrogram based representations there. Now, what people found with wave LM, Hubert, and so on, maybe this you have already found study. If you have studied, what they found was initial layers they are more focusing on speaker and those kind of problems for you. The later layer they more focus on phoneme recognition, automatic. Yes, hello. Um, so they focus on phone recognition and like more high level message related problems. They start focusing on message related problems, whereas the lower layers are they're more like speaker related problems or paralinguistic problems. We could focus on the lower layers in that. Now this is kind of an understanding we have, but we still not have a clear understanding how and what exactly is this self-supervised speech representation models are learning, or what is called the speech foundation models. So what we have been doing is to understand this kind of models. So before I go, I have still, I think, another 20 minutes, 25 minutes. I would like to ask if you have any questions before I get into the some of the studies that we have been doing on speech foundation models. No questions?
Yes, I think there is no question.
Okay. That means either I am very bad at telling my story or it's super clear everything.
I have just one question, Professor. Like you have
Mhm.
mentioned, you are using sinusoidal kernel
Yeah.
in the during analysis phase. So how you are considering the frequency of the sinusoidal signal?
Actually, you're talking about this one, right? Yeah.
Yeah, yeah. This one, yes.
So this is an analogy I'm giving for DFT. So
Okay.
DFT can be seen as a sinusoidal analysis where what you have is input signal X.
Uh-huh.
You project it on any cosine basis. That
Okay.
is what is X comma
Hmm.
FM. And so
Hmm.
this FM is a particular sine or cosine basis.
Hmm.
And
This
you
is
take the
randomly
DFT,
chosen?
pardon?
This frequency is randomly chosen, or you are finding?
No, it is your endpoint DFT, no?
Okay,
You
okay,
ta-
okay,
yeah, you take endpoint DFT, you can draw
okay, okay.
all the
Understood, understood.
sinusoidal for
All
that,
the
right?
different sinusoidal component you have
Yeah.
considered.
So you have endpoint DFT. If you take it, you can draw those all those sinusoidal components,
Okay,
right?
okay,
So what we
okay.
are doing in the DFT is that you are projecting it, and
Hmm.
then if you take the DFT of the sines or cosine, it's going to be a
Hmm.
delta function at that
Yeah,
particular
function. Yes,
frequency. So
yes.
and then you can see what you see as a spectrum is
Hmm.
here I marked here in this equation over here down is
Hmm.
nothing but this projection times the Fourier transform of the sinusoidal component you are looking at there.
Hmm.
So your whole spectrum can be seen as a filtering operation.
Okay, okay,
Now, what
okay.
I am trying to say in this presentation is when I train the CNNs, the first convolution layer, I can analyze it in the same fashion, except that they are not going to be sines and cosines for me.
Hmm. Hmm.
They are going to be learned filters. That's it for
Hmm.
me. I cannot
Okay,
guarantee the orthogonal properties which the bases have and so on. For example,
okay.
the simplest thing I can tell you is that we are giving 30 samples as input to the CNN, the
Hmm.
convolution layer, but we have 80 filters. So the
Okay.
number of FFT points is more than the number of samples, which is not possible
Hmm. Hmm.
for us. We are looking your sorry the signal length is less than the is
DFT point.
much less than the number of filters for you.
Yes, yes, yes.
So you cannot guarantee all these basis properties and so on there.
Hmm.
But what we know from the compressive sensing and sparse coding is that
Yes.
what they could be learning is some form of atoms there.
Hmm.
It not necessarily focuses on one particular frequency. If you take the papers I have cited, we do show that actually it is not going to focus on one particular frequency, but it's going to focus on different frequency regions for you.
Oh,
So we can do this kind of analysis with the CNN based, even with the CNN that we are training. That's what
okay.
I'm trying to point
Yeah,
here.
yeah.
And
Thank you.
then we can connect to the regular spectral analysis and understanding and so on. Yeah.
Yeah,
Is that okay?
yeah, yeah. Thank you, thank you.
Okay. So, so what I'm going to talk a little bit about uh, foundation models, and I believe many did is have you done? I just want. I'm curious about what kind of problems any of you have tried with the wave to vector. I'm sure you would have all tried in some way or other way. Uh, so I just wanted to know if from the audience if they have tried, what kind of problem they tried.
So
Okay, so if,
I
yes,
think,
We
please.
Professor, most of the participants are new researchers, except
Okay,
few faculty members. So
okay,
they might not have used this web vector.
okay.
So
So,
then you
so
can.
okay, so let me go with one step ahead. So what I
Mm,
was trying to show was we are training these self-supervised models, upstream models, and I kind of showed how they could be trained in the Hubert and Wave2, Vec2, and so on. And after that, you're adapting the downstream model. Then you adapt the whole networks. So typically, you see this kind of networks will have like 4 to 5 convolution layers followed by 12 to 24 or even 48 transformer layers in them inside that. Now, when you want to adapt them, you can ask, are all layers meaningful for the task? I don't know. Nobody has an answer for this question, but people, what they do, they try to adapt the whole network. So one way to do the whole network adaptation is but the problem, if you want to adapt the whole network, you need lots of data because they have so many parameters to adapt. So people came up with what's called parameter efficient fine tuning, where you kind of low rank adaptation methods they came, which on top of this foundation model parameters, you learn a few more adaptation parameters, and with them you can adapt to a problem. Again, in this kind of task, like if I want to do speech recognition, I may want to classify phones. If I want to do speaker, I want to classify speakers. You can do this thing, but again, first question is that we need all this? One way to solve your data scarcity issues, so here is what the case I'm trying to present here, is we have a problem where I want to say whether the speech is from healthy control or if the speech is coming from a Parkinson disease patient speech. I want to do that. Now the problem is that we can get a lot of healthy control data for us, but Parkinson's disease data is not, you're not going to have access to a lot of Parkinson's disease data at all. Now, in this kind of problem, just adapting all the layers may not be necessary for you. First of all, we even don't know. We blindly start adapting all the layers. We try to come, oh, every layer is important. This is the assumption we are making. So this is one of the works of Tilak, whose work this work is getting presented in ICASP. So what we try to do is, okay, you take this kind of low rank adaptation methods and you want to compare it to the case where you take different layer representation and train the classifiers. So you free the foundation models, and then you try to take different layers output and then train a classifier for each layer. Now the question is which layer to choose for you. Another approach is that you can fine tune the whole thing without this parameter efficient kind of training and so on. You can do that. So this is another approach. We were trying to compare what happens with the layer selection compared to full adaptation or low rank adaptation, how layer selection work. Now we have to select which layer information we should look at it. So what you could do, we do what's called a cross validation. So to take the cross validation data, you train the network on the training data. You take hidden layer representation H1, which will be layer 1, and you train a classifier to do on those features, healthy control versus Parkinson's disease. And then you can ask how does it performs on some kind of handheld cross-validation data. So I have plotted here, and in this figure you can see that this is that for the wave to vec2 network, this is kind of the 10th layer is more optimal. That's what the cross-validation set is telling me. Whereas in the case of Whisper, if you have, which is a speech recognition problem train network, the last layer is the most important for you. And whereas if you take which is a multilingual large wave2vec, which is trained by Facebook and it is available outside, it is it's the information it's saying is that, oh, you look at the 16th layer output. So this is from the cross-validation data. So what we did, we take these layers and then train this classifier here, and then we are going to compare to the case when we adapt all the networks, or we do this parameter, the whole network completely, or we do parameter efficient fine tuning, which is shown here below, the B and C we were trying to compare. Now, once we did this layer selection and did the testing, what we found, for example, is that Although we found 10th layer to be the best in the wave 2 vector case, is that still performs well, but it slightly performs worse than the layer 3, but still these two performances are closer. What we found, for example, here for layer 16, that for the big XLSR model, the multilingual pre-trained model, what we find that it's almost the same. The 15th and 16th layer, this is what the performance is coming close to. And in the case of Whisper, again, the last layer is the best performing kind of a thing. So what we found is that, okay, there's a way that if you apply some kind of a cross-validation technique, you could figure out which layer is important for you, and then you train the classifier on top of those feature representations. And this classifier can be shallow, simple, shallow networks if you want to train them. Now, here is a kind of comparison. What here present is a big table, but just to summarize, the first one is more handcrafted features. These are traditionally used for paralinguistic representation. And then we can see that no matter what we do with the cells foundation models, all the systems are better than the standard handcrafted feature representations. This is again just reconfirming that these foundation models are indeed learning some representation that are much superior to just taking the handcrafted feature. And then if you do a layer selection and we train the classifiers, what we find is that it comes close to LoRa fine-tuning, kind of low rank adaptation, fine-tuning, it is coming close to that. So what it's kind of trying to show is that whatever we want to do, what we could do is we could actually optimize. You can see the number of parameters marked here. You can deal with a fewer parameter system and still achieve performance close to fine-tuning the whole network. That means it kind of says that first thing is saying that the transformers in the different layers in the foundation model, they may not necessarily be useful for all the tasks, for your task, for all the tasks. So fine-tuning completely this model is a painful job. You will need a lot of data, a lot of resources, but it may not be necessary for you to do that all the way. So maybe looking at which layer is important is an interesting question. Now, the question you can ask, you said, like once you fine tune this kind of model, right? A foundation model, I'm showing here the fine tuning thing. Once you're fine tuning to the downstream task, what you can ask yourself, well, once I fine tuned the model for any task, can it go to, it can still recover information related to another task once you fine tune this model. It's I'll give an example soon, but so why this question came for us is the following. So we were looking at a raw waveform. It goes to the pre-trained neural network. We were getting the embeddings, and from that we were extracting the means, and we were doing emotion classification. So we take this pre-trained network, which is PR, is a pre-trained network. Sorry, pre-trained phoneme recognition. PR is phoneme recognition. So if you take the pre-trained network, which is the FM0 here, and I take the neural embeddings, the last layer neural embeddings, and I take the mean of those embeddings over the utterance, and then I classify for the speech emotion, I get a performance like this. Then I take a neural network that tries to do speech recognition, which is fine-tuned for speech recognition on 100 hours of speech. So it has a phoneme recognition over here, and so you have it is fine-tuned for phoneme for speech recognition task. And even if I take those embeddings and I do the emotion classification, I get a slight improvement over the pre-trained model. But then what we saw was that if you take, okay, now we said, okay, like, why don't we look at 960 hours model, fine-tuned model? Let us look at it. We started, in this case, the phoneme recognition is increasing, but we saw that suddenly that the whole emotion recognition is dropping well below even the pre-trained approach, without any kind of adaptation task. It was well below that. So what we asked ourselves, when we are going from adapting it to, for the speech recognition, does this network completely loses the ability to recover back the emotion kind of classification task and so on? So is it completely lost for us? So what we try to do, so this is the kind of the framework I'm trying to say. So if we have so what we try to ask ourselves, what happens if you take a pre-trained network and fine tune for the task directly? Yeah. And what happens if you take this pre-trained network and you basically fine tune for some intermediate task, which is here speech recognition, and then you try to fine tune that network again for emotion classification tasks? Would these two kind of A and B system, would they come closer to each other or not? In other words, if I'm fine tuning it on big data here for this speech recognition, would it kind of lose the ability to recover, ability to be used for emotion classification problem? So for that, what we did is that, okay, again, you note that this is all wave 2, vec 2, and this kind of model. So the raw waveform is the input. So what we took a pre-trained neural embeddings and build systems with that. We take the output of the task specific embeddings, and then we build the models with that, and then we basically do the fine tuning, and you take the representation, and then you build systems of systems with those features. Again, it is the same formulation here. You get the what is called the functional mean, and then you feed it to a classifier, which is here a SVM model or a random forest model. Now, what we found is the following. Again, so there were two data sets. It's called EmoClap, which has a 4-class classification, and MSP Improve. So there are two emotion recognition corpuses what we studied. What we saw is that if you fine tune the model, the pre-trained model representation for straight away, that is this one, upper A, kind of a thing, you get very good performance on emotion recognition. Then once you have done the fine tuning here, and then you extract the embeddings here. So you fine tuned for speech recognition, you get these embeddings, and then you train with these B embeddings the emotion classifier. They start performing worse than what you do state fine tuning. So this kind of concurs with the idea that, oh, I have moved this problem to speech recognition task, and the performance is dropping. Now, the third here, what I'm trying to show here is that take this network, which was fine-tuned for speech recognition, and then try to fine-tune it for emotion recognition. You get these embeddings. Again, it can be 768 dimension embeddings. Here all are. And you take the functional over the whole utterance, and you try to classify for emotion. What we see is that it's coming back to the same performance as this case, the same. So if you straight fine tuning and this way of fine tuning, we come to the same performance. So in other words, what I'm trying to say is, at some point, it was not so informative of emotion the moment I fine tune, but again, if I fine tune this network, it is able to come back and do emotion recognition. It is able to do emotion recognition to a good extent, again, back as direct fine tuning. So what we looked at, the thing is, in this case is, okay, what's happening? So you take this output embeddings and then you can compare. So what happens if you have fine-tuned for network, you take the embeddings and you can compare it to the case of this case where it is fine-tuned for ASR, or if it the case you can fine-tune it for the after ASR you can fine-tune it for emotion recognition, and you can compare these features. So what happens is that what we found was that for speech recognition system, like when you are fine tuning an ASR, there are many features that we took the cosine distances, right? So we are trying to look at the cosine distances, and what we found was that that there is plenty of data points that's mismatch that speech recognition is introducing at the output layer of the last transform layer for both EMOCAP and MSP improve. But the moment you fine tune those models, um, fine tune those models, what we see, like if you fine tune, that's what here happening. What we find that the decisions that you take with SCR directly with this model straight for fine tuning and ASR followed by speech emotion recognition fine tuning, the decision they don't do, there's not a big mismatch in the decisions. Only like a few frames are like 20-30% of the frames are differing. Otherwise, the cosine similarity is pretty close for once you kind of do this kind of fine tune the ASR system in for the emotion problem. What we also looked at is the attention heads what we have in the layers, and we compared to the cases here. So you take the model, for example, you take this case where you have fine-tuned this model, that A case, and that is what is called SER, and you look at the attention mechanisms, and you take the ASR model, which is this one. It is not fine-tuned for emotion at all. It's fine-tuned for speech recognition, and you look at the attention mechanism of that, you compare that, you see that the first few convolution layer, it's not changing much. They are pretty similar, the attention mechanism. What is happening is the later layer, there is a big divergence between the attention layer. They are differing. The later layer attentions are differing for you. But then once you fine tune this speech recognition model, which is to the speech emotion recognition problem, you see that these attention mechanisms, they suddenly become similar for you. Now we saw the same in the case of fine-tuned model with 100 hours model or fine-tuned model with 960 hours of speech recognition. What we found that even though speech recognition systems are moving this representation at the output layer far away from the emotion problem, the moment we are fine-tuning again those networks, the network is able to come back. It's able to recover its ability to do emotion recognition, similar to the case where we fine-tune directly, similar to the case where we fine-tune directly the network for the pre-trained network. So what it says is that this layer, the informations that are stored in this that are stored in this kind of models, they are recoverable. They don't suddenly, if you fine tune, they don't lose completely the information about other tasks, so they could be recovered. That's what this is kind of is trying to demonstrate over there. Now, Om, um, you have 5 minutes, 10 minutes. How much you have for me?
Yes,
And
sir.
this because
You can maybe, sir, summarize maybe by 5 minutes, sir.
yeah, Okay, so I just wanted to give you some some point about um, um, I don't,
Aspects of the sublime in
so maybe the
deep
TPS. So that the text to speech synthesis, I can skip that, and maybe a little bit thing I can say about, okay, can we, what we were looking at was, okay, the speech foundation models, they are not making any big assumption about speech production or speech perception, all those kind of a thing. They're trying to learn some information directly from the signal. So we can expect, so can these models be used for bioacoustics analysis? So instead of humans analyzing the human voice, you can analyze vocalizations of animals, for example. So we asked this question. So this foundation model that are trained on human speech, can they be useful for analyzing animals' voice? So so what we did is our initial analysis for 2 years back is that we analyze it for marmoset, which is a small monkey here, and it has calls uh, like 1, 2, 3, 4, 5, 6 about. It has a vocabulary or call set about 16, but here not all 16 are visible for you. Is there, and this is the set of marmosets and how much they are producing each calls. There are different types of calls, and it kind of, you see that the marmoset calls are very short durations. It goes from 100 millisecond. Very rarely it will go to 1 second speech for you. Can sorry, 1 second vocalization, and you want to figure out whether we can distinguish the callers. So what we did, it's a very simple method. Here I try to summarize. So you take this marmoset audio, you feed into the what is called to the self-supervised learning model, right? And then what you can do is you can extract this feature representation that comes at the output, and you treat them, see them as a single Gaussian model. So you estimate the means and the variances. For each speaker, you estimate the means and variances each time you give a particular speaker, and you can compare the distributions of the Gaussians to detect whether, to say whether these two distributions are of the same marmoset color or not. So here is the case like 1 and 1, it is the same marmoset color. 2 and 2, so the diagonal is the same marmoset color, and the other points of the diagonal is you are comparing different marmoset colors. So what we found that these features, this just analyzing them just with a Gaussian distribution and asking whether they can distinguish between the colors, we see that they are able to distinguish between the different marmoset colors here. Whether I use Bhattacharya distance to compare these Gaussians or whether I use KL divergence, doesn't matter. In both cases, we see that the distributions as they are the colors wise you can distinguish based on the distribution. That means even though this network is trained for human voice, we could potentially use them for analyzing animal vocalizations and everything. So what we did some kind of caller detection analysis. So we took a series of many. So here I'm showing it on one such wave LM network, this analysis, but we looked at all different types of models that were trained, self-supervised learning models, and we applied this caller detection analysis, and we found that it's pretty well, it does pretty well. Uh, Irrespective of which kind of foundation model I take it. So what we see is that for all callers, we were able to get above chance detections. So you want to say if a given speech is of caller ID 1 or not. Like this, you are asking this kind of speaker caller detection. In this case, I'm calling caller detection instead of speaker detection. And you are able to get above chance. And irrespective of which embedding extractor you are using, we are able to distinguish detect the callers. And we see that all this, if you put the number of parameters for each of these self-supervised model, and then you look at the performance. The performance range is not a big way differing, but whether it is more parameters or less parameters, it was not making us a big difference. It was trying to show that this kind of networks, what we have learned on self-supervised speech foundation model, the self-supervised learning-based model, although they are trained on humans, they can be still useful for analyzing bioacoustics or signals for us. And the reason for that is, which is not demonstrated that carefully yet, is that no matter what you do, this network should be somewhere learning some spectrotemporal patterns. And even in animal vocalizations, these spectrotemporal patterns are the ones which are going to convey information to you. So if you have learned it on different type of audios and the spectrotemporal patterns, it could be useful for animal call analysis. So to summarize, what I'm putting is that what I've tried to convince you all is that you could learn representation directly from raw signals. We not necessarily we have to go through Fourier transform and applying source system decomposition knowledge and so on. So that the first part of the talk, I try to convince you that it is indeed possible. The foundation models are building on that idea to the level that you can build it, that we can train big networks that can exploit lots of data, and you can just fine tune those models for downstream problems. But as I was trying to point out, are all layers meaningful for all tasks? Certainly not. How to find that out? So this is what I showed one example how we could find out. For example, we have carried this analysis for animal vocalization, and we always have seen that the first few layers, like first 1, 2, 3, 4 layers, they are more useful for animal vocalization analysis than the later layers there. How do we efficiently adapt? This is still a problem for us. These models are too big. How to compress these models is also an open problem. What I showed here, and you would have realized that already, that there's nothing much I can explain you what is happening with these models. So interpretability, explainability, what kind of information are the layers modeling, and how, why and where the model fails. Suppose what happens is that you have a big network, suddenly it doesn't work. What will you do? Shall I throw it out and adapt or train a new one, or try to fix it? I don't know. I really don't know how to do that. This is a problem. Second, then there are a lot of trustworthiness. How reliable? Because we cannot interpret them, we cannot explain them. So how much we can use this the kind of models to build trustworthy system? And then there is a big trust. Well, we are saying we want to do any kind of task with this self-supervised learning model. Is it feasible with one single speech foundation model? To me, it is not a feasible problem, but unless somebody is ready to show me that it is indeed the case. But what it is presenting us is an opportunity to better understand the speech information if we can dig in them little by little. And right now, most of the works are stopping at the performance level. There's less of explainability there. I'll stop here. Thanks. I'm sorry for overshooting the presentation here and for the delay in starting the presentation. Thank you.